Welcome to Pre-Calculus. Today we will investigate transformations of the rational parent function 1 over x, focusing on how changes to the parent's equation change the parent's graph. Let's take a look at one example that involves multiple transformations. So here's our first example. It's the parent function f of x equals 1 over x. And the transformations that we want to make on that function are multiplying it by half, subtracting 2 from the domain value, the x, and then adding 1 to the range value, the f of x. So we want to graph the transformation, but before we do that, I want to graph the parent function so that I can do this first task, describe the changes I think the transformation makes on the parent's graph. So I should see the parent's graph first. So we'll do that by creating a table. And the nice thing about graphing a parent function is it's very quick. So I'm going to give the x values -2, -1, 0, 1, and 2. And then we'll calculate 1 over x. So we'll start in there. 1 over -2 is -0.5. 1 over -1 is -1. So I see both those values are going to be below the x-axis. At 0, I have 1 divided by 0, and that's classic undefined. And remember, when you're looking at the table of a rational function and you see undefined, typically that means you've got some kind of discontinuity. In this case, it's a vertical asymptote. On the right side of 0, we got 1, so 1 over 1 is +1, so that's now above the x-axis, and then at +2, 1/2, +0.5. So we'll graph this parent rational function. Definitely we've got a vertical asymptote at the y-axis. We also have a horizontal asymptote, and its default position is at the x-axis. And then I'll graph these 5 points. So -2 is at -1/2, -1 is -1, +1 is +1, +2 is +1/2. And I'm going to sketch that parent function. So this lower piece of the graph is in quadrant 3 entirely. Gets close to those axes, but it never touches them, never crosses them. The right-hand piece is entirely in quadrant 1. Similar situation, it gets close to the y and the x-axis, but it never touches, never crosses. So that is my parent function. So what I want to do next, now that I have the graph of the parent function in view, is describe the changes that I see have been made to the parent function's equation. So my transformations are given by the rule 1/2 times f at x -2 plus 1. One thing I could do is apply these 3 transformations to the actual equation of the parent. So I want to do that. We're going to call this g of x. So it takes the parent, and if I have the structure 1 over x, one thing that I see is that I need to subtract 2 from wherever the x is. I need to multiply by 1/2 out front, and then I need to add 1 on the far right. So that's really the equation that we're working with. It's 1/2 times 1 over x -2 plus 1. So I want to describe those changes and say, what are they going to do to this parent function's graph? So we'll start with the -2. That is a left or right hand shift, a translation. So I'm going to note that horizontal translation is opposite the sign. So the idea is if it's saying -2 like we've got here, minus is typically to the left. However, in a translation, when we're considering the transformations, we're going to go opposite the sign. So my prediction is that it should move the graph 2 to the right. That's one of the changes. I also have a +1 that's really tacked on to the end. That is a vertical translation. And we need to remember the distinction with a vertical translation, unlike horizontal, we actually follow the sign. So if we're seeing +1, plus in the vertical dimension typically means up, and that's how we're going to predict that this should move the graph up 1. The last change I see here is that we've been multiplied by a factor of half. Now, that factor has the potential to do one of two things to a graph. It can either shrink it down vertically, and that's the case that we're seeing with this half. So it's when your multiplier is between 0 and 1, that is a vertical, kind of a descriptive word is a shrink, but the technical word is a compression. And basically, I think that's going to make the graph become flatter. We should put the other possibility that A is bigger than 1. In that case, if that were like a 2 or a 3, that's a vertical stretch. And what we would predict the graph to do in that case is become elongated, more thin, more narrow, and tall. So that kind of gives me an idea about where things are going. I'm going to go ahead and predict where the asymptotes and the graph itself are going to move. So if I'm moving to right, what that's really going to change on my graph is my vertical asymptote. So it's going to move from the y-axis over to the position x equals 2. If I'm moving the graph 1 up, the horizontal asymptote is going to shift from the x-axis to a 1 higher position at y equals 1. And then the vertical compression should make the graph tighter in to those axes. So instead of having a gap kind of between the axes, I should see it get compressed down, especially towards that horizontal asymptote. So I made some predictions. What I need to do now is prove them by regraphing the function. So what I'll do is let's graph this one in green so that we can see it distinct from the parent function. So here's x. We'll go ahead and choose the same, at least to start with. Although, in fact, we could be kind of wise about this and just change our domain based on the shift that we saw horizontally. So if I'm shifting the whole function 2 to the right, I could start at 0, 1, 2, 3, and 4. Let's see if that works. And then we'll calculate our actual function. Let's put it here in the orange. This is half times 1 over x minus 2 plus 1. So what we're ready to do is to graph that. So let's take this over to the calculator Desmos to help us get a table. With a complicated transformation, you kind of can save time going to a calculator. So I think that's a wise choice. Let's head over to Desmos. So I'm going to type the new function in. This is the transformation g of x. So it's half times 1 over x minus 2. So you can see the horizontal shift there. And then plus 1. And so we can see our predictions are pretty accurate. What we need is a table, though, to graph this. So there's our table. And as you can see, our initial domain, -2 through +2, wouldn't really catch any of the right-hand part of the curve. So I'm going to go back and delete so that I'm just starting at 0. And then I'll include 3 and 4. So at 0, we've got the value 3/4. At 1, we have the value half. At 2, we have an undefined, that's our vertical asymptote. At 3, 1.5, and at 4, 1.25. So we'll take our table back to our note screen to finalize our own graph. And those values that we just copied in, we're going to repeat here. 0.75, half, undefined, and that's the vertical asymptote, 1.5, and 1.25. So let's graph the transformation. And again, we're looking to see, did our predictions, did they describe how the changes in the equation change the graph? So at 0, my value is 0.75. At 1, the value is 0.5. So on this left side, we definitely see that the function has gone 2 to the right, 1 up. And notice it's much closer in terms of being tight to the asymptote than the original parent function. That's a little tricky to see, but we can definitely see that in the points and on the graph once we plot that. At 3, it's at 1.5. And at 4, it's 1.25. Everything's closer to the horizontal asymptote. And I'll go ahead and label that green one is my transformation. And it looks like the 3 predictions we made check out very well. So I do have that horizontal translation 2 to the right. I've got a vertical translation 1 up. And I've got a vertical compression by a factor of 1/2. Well, thank you for joining for this investigation of transforming rational parent function. I'll let you transform your own rational parents. See you soon.